Hey kiddos, today we're going to be talking about a lot of stuff. We're going to be talking about tangents, and then we're going to talk about interior and exterior angles. So, first let's begin with tangents, and we're going to talk about a particular situation of tangents being perpendicular. So, if a line is a tangent, which we should hopefully recall tangents are on the outside of the circle and they touch only at one point called a point of tangency. Okay, so if a line is a tangent to a circle, then it is perpendicular to the radius that would be drawn to the point of tangency. So RT is a tangent, which then would mean that RT is perpendicular to CT, because CT is the radius. The converse of that would be that if CT is perpendicular to RT, then RT has to be its tangent. There's a little logic thrown in there for you. All right, so let's look at an example of this. So here's our first problem. I can see I have the tangent BG, and I see that my radius is UB. All right, and I see I have not just a radius here, but it's an extension of the radius to connect to the tangent. So one thing I can note is that this little piece right here, from here to here, would be 8, because it is a radius. But notice they tell me that the whole thing is 14. We're going to use our rules. Because this is a radius and that is a tangent, we can see that they are perpendicular. So that means it creates a right triangle for us. So that means we can use Pythagorean theorem to figure out what the value of x is, which is from B to G. Okay, that's what we got to figure out. So, in setting up Pythagorean theorem, we'd have 8 squared plus x squared equals 14 squared. All right, 64 plus x squared equals 196. Subtracting 64 from both sides, you get x squared equals 132. And of course, last but not least, take the square root of that, and x equals approximately 11.49. All right, now let's look at this next question, next problem. Notice here they have it already set up for us, and the question is PG actually a tangent? So meaning, can we actually justify putting a right angle at this point, because the radius is supposed to be perpendicular to a tangent? So we need to check to see basically if Pythagorean theorem is going to be true for this case. Now, I hope that you guys notice that this little section right here is 8, meaning it is not this whole thing. So that little piece right here is the radius, which is 7. So notice I put a 7 here. So this part right here is really 7 plus 8, which is 15. So let's see if Pythagorean theorem would actually work here. I have 7 squared plus 13 squared, and it's supposed to equal 15 squared. All right, 7 squared, 49, plus 13 squared is 169, equals 15 squared, which is 225. 49 plus 169, 218 equals 225, which, nope, that's not true. So is PG a tangent? The answer is no, okay? And the reason why is because Pythagorean theorem did not work for this situation, so therefore PG is actually not a tangent. All right, so this next part, looking at congruent tangents. So when can tangents be congruent? If two segments from the same exterior point, so notice when we refer to exterior point, that means it's outside of the circle. So D is exterior point because it's outside of our circle, okay, are tangent to a circle, then they are congruent. So therefore, because tangent BD, and I can prove that it's a tangent because I see that it's perpendicular to the radius, So BD is a tangent and AD is also a tangent. So because both of these tangents are coming from the same exterior point, then they are marked as congruent. So BD is actually congruent to AD. All right, let's look at an example. All right, so here we have TS and US are tangents. And we can clearly see that because they're perpendicular to the radius. So that checks out anyways. Which then means that TS and US, since they share the same exterior point, they are congruent to each other. And TS is 7x minus 3 and US is 5x plus 1. What is their measure? All right, all we have to do since they're congruent is basically set them equal to each other. So you get 7x minus 3 equals 5x plus 1. All right, we are solving for x. So I'm going to subtract 5x to both sides. 2x minus 3 equals 1. Then we're going to add 3 to both sides. 2x equals 4. Last step is to divide both sides by x, and x equals 2. Not done, because we're actually going to try and figure out what is the value of TS and US. So all we have to do is take this value and plug it in. So let's look for TS first. And TS is 7x minus 3. So I'm going to substitute in the 2 for x. So 7 times 2 is 14 minus 3 means that TS is equal to 11. And because they are congruent to each other, US would also equal 11. Yay! All right, now let's move on to interior angles. So we're going to deal with interior angles first. Now, we already know at least 2 types of interior angles, and that's the central angle and an inscribed angle. So what we're referring to now are interior angles, so they're inside the circle, but they're not at the center and they're not on the circumference either, okay? So for example here, angle 1 is considered an interior angle for this particular circle. So if an angle is formed on the interior of a circle, so not at the center, okay, its measure is equal to 1/2 of the sum of the measures of the arcs intercepted by the angle and its vertical angle. Okay, so in other words, to find angle 1, it's 1/2 of the measurement of arc AC plus the measurement of arc BD. So another way to write this formula, okay, if you don't like to deal with fractions, is basically measurement of AC, arc AC, plus the measurement of arc BD, and then divide that by 2. All right, so looking at our first example here, we are given, okay, the measurement of BD, arc BD is 55, and the measurement of arc AC as 75. And we need to find the measurement of angle 1 and angle 2. So, because angle 1 is an interior angle, and it corresponds to these 2 arcs, it's intercepted by these 2 arcs, okay, I'm going to find that one first. So, formula states that I would take the measurement of arc AC plus the measurement of arc BD and then divide that by 2. So when I substitute that in, I have 75 plus 55 divided by 2. And when I work that out, that's 130 divided by 2 gives me 65 degrees. So the measurement of angle 1 is 65 degrees. Now, hopefully you don't forget prior knowledge here. This is a straight line. These 2 angles are adjacent on a straight line, which means they add up to 180 degrees. So if angle 1 is 65, I just need to subtract that. So 180 minus that 65. That will give me the measurement of angle 2, which is 115. So basically, 180 minus the 65 is how I worked that one out, and that gave me 115 degrees. All right. Moving on to the exterior angles. Well, should be pretty straightforward because exterior would imply that it means it's outside of the circle. So as you can see here, angle 1 is located outside of my circle, so therefore it is called an exterior angle. If an angle is formed on the exterior of a circle, its measure is equal to 1/2 the difference of the measures of the arcs intercepted by the angle. So notice it's going to always intercept two arcs. So for interior and exterior, there's always two arcs that it's going to intercept. Interior, you add them. Exterior, you do the opposite and you subtract. Okay? Always subtract the bigger arc measure from the smaller one. I'm just to clarify. All right? So to find the measurement of angle 1, it's 1/2 times the measurement of AC minus the measurement of BD. Or the quicker way I think to write it would be the measurement of arc AC minus the measurement of arc BD, and then just divide that by 2. So let's look at an example. All right, so for this first problem that we're looking at, we are looking for the measurement of angle 1, or angle URE, okay? And we need to determine if we know the measurement of the arcs that intercept it, which I'm going to highlight. So I see SM is one arc that intercepts that angle, and I also see that UE would be the second. Remember, there's always two. Okay, so according to the formula, I would be taking the measurement of arc SM, because it's the bigger one, minus the measurement of the smaller one, which is arc UE. And after I subtract them, I would divide that by 2. So they already give me the values I need. So the measurement of arc SM is 120 minus the measurement of UE, which is 50, and then divide that by 2. So we get 120 minus 50 is 70. 70 divided by 2 is 35. So the measurement of angle 1 here is 35 degrees. So that right there is 35 degrees. All right, now let's look at the second example. Now, again, we're looking for the measurement of angle 2, which is this angle right here, my exterior angle. And I need to locate which arcs are intercepting that exterior angle. First one I get is this one here, FH. All right, and then the second one is this one right here in red. Okay, now I have the measurement of arc FH is 215. And I'm going to add a letter here so you guys can kind of see where I'm going with this. So the measurement of arc FH, because that's the bigger one, minus the measurement of arc AB, then divide by 2. Now we know the measurement of FH is 215. It's given to us. But they don't give us the measurement of arc AB here, this little piece. Now, the nice thing is there's only one other arc that's in this circle, and that's FA, which is 83. So I know that the total degrees of a circle is 360 degrees. So if I just take 360 and I subtract the 215 and subtract the 83, what I'm left with has to be what I'm looking for, which is 62. So the measurement of arc AB is 62. So now that I have that, I can plug it into my formula, which I get 215 minus 62, and then divide that answer by 2, and I get 76.5 degrees. So the measurement of angle 2, that exterior angle, is 76.5 degrees. All right, I believe that's a wrap. Awesome sauce. Ciao.